In this video, we're going to continue integrating with hyperbolic functions. We're going to do a lot of integration by substitution and derive two more standard results for us to use. So we're going to start off with this question. It says, by using an appropriate substitution, find the integral of 1 over the square root of x squared minus a squared. Well, the substitution I'm going to use is going to be x equals a cosh u. The reason why I'm doing that is I'm looking at the denominator of this integral and I'm thinking about how I can simplify that. Now, I know that if I substitute a cosh u into this, I'll square it, so I'll get an a squared cosh squared. I will then be able to factorise out the a squared, which will leave me with a cosh squared minus 1, which I know can be replaced with sinh squared, which will then get square rooted and it will all simplify nicely. So that's why I'm going to do this substitution. So let's actually do it. So we all know that when we do integration by substitution, we first have to do a little bit of differentiation. So I'm going to differentiate both sides with respect to u. Cosh differentiates to be sinh. So dx will get replaced with a sinh u du. Dx here gets replaced with this. Right, let's do some substitution. So the integral of 1 over the square root of x squared, so that's going to be a squared cosh squared u, minus a squared times dx u du. Let's do those steps of simplifying the denominator. Just simplify my numerator first. So on my denominator, I'll factorise out the a squared and I'll be left with cosh squared u minus 1, which will then simplify to be sinh squared. Cosh squared minus 1 is sinh squared. I can now square root the denominator, so the square root of a squared sinh squared will just be a sinh u. So I'll get a sinh u du over a sinh u, which cancels out to be the integral of 1 with respect to u, which is u, plus my constant. I now need to remember that I can't leave my answer in terms of u. I need to swap it back to be in terms of x. So I'm coming back to my substitution here, and I want to make u the subject. So I'll divide both sides by a, and now do r cosh of both sides. And so the answer to my integral, instead of u, it's r cosh. That is the answer to this integral. And this is a standard result. One of two standard results, the bottom one there. So I've just proved the bottom one by doing the substitution of x is equal to a cosh u. You can do the top one by doing the substitution x is equal to a sinh u. The reason why that will work is because you will then have an a squared plus a squared sinh squared, which then the a squared will cancel out, will factorise out to leave you with a sinh squared plus 1, which can then then be replaced with a cosh squared. And it will all simplify nicely, and you'll get your nice integral as r sinh x over a. So these are two standard results that we now know. And in fact, they are more generalized versions of the ones we saw in the previous video. We saw that if this was 1, if a was a 1 here, then we just got r sinh x. Or if a was a 1 here, then we got r cosh x. So these are more generalized versions of the results we saw in the previous video. So let's do an example using one of those results. I've just copied the relevant result in the bottom right hand corner there. I want to have the integral, I want to show that the integral from 5 to 8 of 1 over the square root of x squared minus 16 with respect to x is ln 2 plus root 3 over 2. So I'm using the standard result from the formula booklet. We can see that a squared is 16, which would mean that a would be 4. So I can just straight away now write down that the answer to this integral is r cosh x over 4. Now I just need to do some work with the limits. So I'm going to substitute the 8 and the 5 in. So I'll get r cosh 8 over 4 is 2 minus r cosh 5 over 4. Now remember the logarithmic definition of r cosh. We had r cosh x is equal to ln x plus the square root of x squared minus 1. So for r cosh 2, if I substituted 2 here, I would get ln of 2 plus the square root of 2 squared minus 1, which is 3. Now I'm going to substitute 5 over 4 into the r cosh, and I will get ln 5 over 4 plus the square root of 5 over 4 squared minus 1, or 5 over 4 squared minus 1, 25 over 16, take away 60, that's going to be 9 over 16, which when I square root it would be 3 over 4. Five over 4 plus 3 over 4 is 8 over 4, or 2. And now I can use my laws of logarithms to bring these two things together in the required form. So that's a relatively simple example of using the standard results. Now we're going to do a few more examples of different integration by substitutions with hyperbolics. So I need to show that the integral of the square root of 1 plus x squared is all of this stuff. The substitution I'm going to pick here is going to be x is equal to sinh u. The reason why I'm going to use that substitution is if I substitute sinh u here, then I will end up with 1 plus sinh squared, which can be replaced with cosh squared, which can then be square rooted nicely. So do some differentiation first. Okay, now let's do some substitution. So the integral of the square root of 1 plus sinh squared, replace the dx as well. So I get that. The 1 plus sinh squared can be replaced with cosh squared. The square root and the squared cancel out to just be cosh. And so I just get left with the integral of cosh u times cosh u, which is cosh squared u du. in order to integrate that, I need to use the double angle formula. So give me a moment because I'm going to need quite a bit more space. So let me just create some more space with this. I'm still going to need my substitution, so I won't rub that out. Okay, so we want the integral of cosh squared u du. Right, let me write the cosh double angle formula over here. We know that cosh 2u is 2 cosh squared u minus 1. So making cosh squared the subject, I will get cosh 2u plus 1 all over 2. So that's the integral I'm going to do. I'm going to take the half outside, and I'll have the cosh 2u plus 1 du. Integrate cosh to get sinh, but I will need to divide by 2 because of the 2 on the inside there, the reverse chain rule. The 1 is going to integrate to be u. So all of that is going to simplify to be 1/4 sinh 2u plus u, plus half u plus c. Right, so we've integrated this, but I've got it in terms of u and I need it in terms of x. So again, I need some more space to help me out with this. So just bear with me again. So I have got the 1/4 sinh 2u plus a half u plus c. Right, now the awkward thing with swapping this back to be in terms of x is that my x substitution was in terms of sinh u, not sinh 2u. So I need to do something with this 2u. I need to use the sinh double angle formula to expand that out. And that's okay. I know that sinh 2u can be replaced with 2 sinh u cosh u. The quarter and the 2 will simplify to be a half. Now, the sinh, well, I can replace that easily. That's just x. The cosh, I need to replace that as well. Well, that's not too bad because I know that cosh squared u is going to be sinh squared, oops, written that the wrong way around, sinh squared u plus 1. So therefore I know that cosh is going to be the square root of sinh squared plus 1. And given that I know that sinh u is x, this allows me then to replace the cosh with x squared, the square root of x squared plus 1. So let's do those. So I've got the sinh gets replaced with the x, the cosh gets replaced with the square root of x squared plus 1. Then I've got the half u. Now remember that the original substitution was x equals sinh u. So doing r sinh to both sides, I get that r sinh x is equal to u. And there we go. This is the answer that we were required to show. Right, we've got 2 more examples to go. So this question, by using a hyperbolic substitution, evaluate the integral from 0 to 6 of x cubed over the square root of x squared plus 9. The substitution I'm going to use is x equals 3 sinh u, because when I square it, I will get 9 sinh squared u plus 9. The 9 will factorise out, and I'll be left with a sinh squared plus 1, which will get turned into a cosh, which can then be square rooted nicely. So that's my logic. So let's do some differentiation. Dx by du is equal to 3 cosh u. So dx is equal to 3 cosh u du. So I'm going to replace this dx with that. The other thing I need to think about here is the limits. So when x equals 0, my lower limit, that's going to mean that 3 sinh u is equal to 0. So sinh u would equal 0, and u will be r sinh of 0, which will be 0. When x equals 6, I'll get 3 sinh u equals 6. 6. So I will get sinh u equals 2. So u would equal r sinh of 2. So that's my upper limit, and my lower limit is 0. Notice I've highlighted sinh u equals 2 and that u equals r sinh 2, and the reason for that will become apparent a little bit later. Right, let's do some substitution. So the integral from when x was 0, u is 0. When x was 6, u is r sinh 2. My x cubed is going to be 3 sinh u cubed. My denominator is going to be the square root of x squared plus 9. My dx is 3 cosh u du. Now let's do some more work on this and simplify. So let's cube out the numerator, and I'll get 27, because the 3 cubed, sinh cubed u. So let me replace my numerator there. So it's going to be 27 sinh cubed u. My denominator, well, first of all, I've got the 9 sinh squared u. That's from expanding the 3 sinh u all squared, plus 9, which would then factorise to be 9 lots of the sinh squared u plus 1. And the sinh squared plus 1 can be replaced with cosh squared. So my denominator is going to get replaced with that. Which I will then square root to get 3 cosh u. Which then cancels out with this 3 cosh u nicely, to leave me with the integral, I'm going to take 27 outside, of 0 to r sinh 2 of sinh cubed u du. Now, we saw how to integrate this in the previous video. We saw to integrate sinh cubed, what we needed to do was to split it up into sinh squared times sinh, and then turn the sinh squared into a cosh squared, and then we went from there. Now, I'm just going to write down the result. I'm not going to go through all of that method again, because I did it in the previous video. So I'm still going to keep the 27 at the front there. And the result from the previous video was 1/3 cosh cubed u minus cosh u. That is the answer to that integral. My limits are r sinh 2 and 0. Now we just need to substitute our limits in. Now, substituting the r sinh 2 into this could be a bit awkward. This is the reason why I kept sinh u equal to 2 there. Because if sinh u equals 2, then remember that means, remember that cosh, oh, too big. Remember that cosh squared u equals sinh squared u plus 1. So therefore our cosh u equals the square root of sinh squared u plus 1. And sinh u is 2. So I got the square root of 2 squared plus 1, which is root 5. So the point of this is, instead of trying to substitute r sinh 2 in here and here, I've just figured out that actually r sinh 2 is the same thing as cosh u equals root 5. So this is root 5, and this is going to be root 5 cubed. So if I now do 27 on the outside, I've got the 1/3 times root 5 cubed minus the root 5. Then I'm going to substitute the 0 in. So I've got 27, lots of the 1/3 of cosh 0 cubed is going to be 1/3. And then cosh of 0 is going to be 1. All of that's going to simplify nicely to be that. Right, last question. Now, when you look at this, notice that the denominator is nothing like our standard results that we've seen so far. In fact, it's much more complicated because we've got a 12x there. All the previous examples we've seen have been like an x squared minus an a squared, or an x squared plus a 9 or something like that. There's never been an x squared and an x term. So in those cases, in any case where we have an x term as well as an x squared term, we're going to complete the square. So what I'm going to do is I'm going to take that denominator, the 2x squared plus 12x, and I'm going to complete the square. So just bear with me. This should all be very familiar to you, so I'm not going to explain this too much. Hoping I'm not making any silly mistakes here. So I've got that. So I'm going to replace my denominator with this. Right, then what I'm going to do is I'm going to factorise out this 2. I'm going to factorise out a 2 from here and here. Factorising out a 2 will give me a 1 over root 2. Like that. And then I can take that 1 over root 2 outside the integral. Okay, so the whole point of completing the square and changing the denominator like that is the fact that I have now just got x appearing once on the denominator. And in fact, I've got this into a familiar form. I've got my, if you ignore the plus 3 for a minute, I've got an x squared minus 9 inside the square root, which is actually similar to one of the standard results we saw earlier. So to finish this question off, let me just clear some space. So the integral that I'm actually going to try and do here then is I've got the 1 over root 2 on the outside, and I've got the integral of 1 over the square root of x plus 3 all squared minus 9 dx. So what I'm going to do now, I don't want that to be an x plus 3. I'm going to use a little substitution to help me here. It's quite a simple substitution. I'm going to say u equals x plus 3. So therefore du by dx is equal to 1, and so du equals dx. Right, the good thing about this is on my denominator now I will just have a u squared minus 9, and my dx is replaced with du. I can now use the standard result easily to integrate this. This is going to become r cos u over 3. Plus my constant, and now I just need to replace the u with the x plus 3 here. So let me just do that quickly to finish this problem off. And we are done. So if you have an integral with a quadratic on the bottom there inside a square root, if you have an x term, then you need to complete the square to get it to look something like this, and then use a substitution so that you can use a standard result.